Oh, let me get my OBS. There, another one. And there, yeah, iPhone. No, I did not forget. I was running to my daughter and now I'm back. Okay. What else do I need to do? I need to share the screen and there and Windows. Which the screen? No, wrong one. This one. This one. Okay, that's better. So today, what we're gonna learn is something called probability, which sounds like the art of how to scam people that do not know math. Yes, I have a little daughter. That's why I did not teach discrete last term. Probability. Okay. Okay. So there is something about our brain that is wired to reason about probability a bit wrong. But let's start with something that most of you, maybe some of you have seen this already. Most of you are going to get it wrong. I got it wrong on the first try. Okay, so the game is simple. The game, you have 3 cards. Okay, you have 3 cards. Okay, and under one of them is, I don't know, is a joker. Let's say I know that this guy is a joker. You don't? Okay, I know, or only I know. Ajahn knows. Okay, that the joker is here. There are 3 cards. Okay, so your job is to do the following. I ask you, where is the joker? You have no idea. The card is face down, right? So you have no idea. The card is face down. Okay. Or the card looks the same, the card is face down. And then they ask you, which one is the joker? Of course, you're gonna pick one, right? You're gonna pick one. You could pick the joker right away. Okay. You could pick the joker right away, or you could pick a non-joker. Okay. Or you could pick a non-joker. It doesn't matter which one you pick. Okay. Then, so let's say you pick a card. Hope that there is a joker behind. And then what I'm gonna do, because I'm guaranteed, right, to have at least one card that is non-joker. Right? I guarantee to have one card that's not joker. Okay. I have one card that's guaranteed to be not joker. If you pick a joker, then I have 2 non-jokers. So I'm gonna open a card that is not a joker. Okay. So that means, yes, you are learning about probabilities, but we are starting with a problem. Okay. I'll recap that again after I explain all the rule. So I open a card that's not a joker. So by then you will know that, okay, Ajahn, this guy is gone, right? This guy is gone. Are we good? This guy is gone. Which means, and then I'm going to ask you one important question. Do you want to switch your choice? This is a famous problem. You might have seen it in number 5 and whatnot. You might have seen it already. Do you want to switch? But a lot of you probably have never seen it. Do you want to switch? Okay. Or the question is, should you switch? Right? So the question is, should you switch? Right. The name of the problem is called Monty Hall problem. It is an actual game show. Okay. It was an actual game show in probably 1970s, 1980s. And there was a big debate in America about this. And there was a woman whose IQ is like 200 something, try to convince everyone else in America, you know how smart American people is. They believe in like vaccine is bad for you and such and such. But they try to convince, so she got a death threat for a whole bunch of people that you're a woman, what do you know, and things like that. So way back then, you know, people are racist and sexist and like every is, you know. Okay, but the question is, should you switch? So let's listen to all the arguments. What do you think the probability of getting it right if you switch and not switch? The first argument, let's hear me out. The first argument is, wait, if you are here already, there are two choices, right? So that means whether you switch or you don't switch, the probability is a half. Okay, so the first argument, everyone is with me, right? It's a half. Because you either switch or you don't switch, and you have two choices at the end. Right? So the probability is a half. That means it doesn't matter whether you switch or not switch. Are we good? Are we good? Is someone with me so far though? That's the argument. Because you have two choices, right? Switch or not switch. Okay. Right? Because you have two cards. Whether you switch or not switch is like 1 in half, 1 in 2. So it doesn't matter. But think about this. There's something wrong. There's something wrong with this argument for sure, right? But because if you think about it, does the game count rounds? No, just one round. You only have one round. Okay. So the next argument is the following. How about Ajahn? What if I stick to the card that I never really that I stick to the card that I picked the first time? Right. So okay. Let me recap the argument again, because there was the argument was the following. The first argument was that at the end, when they ask you to switch or not to switch, right, you have two choices. So probability is a half, which means it doesn't matter whether you switch or not. Yes. So that means it doesn't matter. Okay. But the other argument is the following. The other argument looks like this. So the other argument is, what if I pick this card, right? I pick a card and I never listen to what Ajahn was asking at all. Right? I never listen to what Ajahn is doing. Ajahn open a joker, I don't care. Ajahn asked me to switch, I don't care. I'm just gonna stick with the first card. I don't even listen to the question that I asked, that Ajahn asked, right? Then what's the probability that the card you pick is the correct one? It's gonna be 1/3, right? 1/3 for not switching, and you don't even listen to me. For not switching and not even listen. Are we good? Are we good? There are two arguments, and they seem to be in conflict because one of them said a half, the other one said a third. To understand this, it's important that you understand the argument. The argument is the following. Yes, and you should be confused. But you should understand the argument, but you should be confused about why is there a conflict. Okay, so let me recap for those of you who came in late. So Monty Hall problem. Why are there only 15 people here? They dropped the class or what? So the problem that we're asking is about Monty Hall problem. You have 3 cards. One of them is a joker. You don't know which one, but I know. Okay, you pick a card. You pick a card, and then I open the card that is not a joker. I guarantee to have at least one of those. Okay, and then I ask, do you want to switch your choice or not? Okay. So the first argument is the following. The first argument is that because at the end, when they ask you already, do you want to switch or do you not want to switch? You have 2 choices, right? So that means the probability is a half. Sounds clear, right? That's the first argument. That means if you don't switch, the probability is a half. If you switch, the probability is also a half. But the other argument, let me call this argument A. Let me call this argument B. Okay. The other argument says the following that, okay, Ajahn, if I pick this and I never listen to all the questions that you ask for all the action that you do, the probability that I'm going to be right is 1/3. Right? Think about this. A says there's probably a half that you're going to get the correct card. B said there's a probably 1/3 that you're going to get a correct card that you never change. Which one is right? 2/3. Okay, you combine the two. No. What do you think? What do you think? 1/3 plus 2/3, and half plus 1/3. If you keep adding, eventually it's gonna be over more than one, right? So when they ask you about probability, make sure it's non-negative and is less than 1. Okay. Now what? So if you choose submit, I open the right, and then you get to choose whether you want the left or the middle. Because I opened the right already, you don't want to pick it. There'll be 2 rounds of selection. It doesn't matter. I only care about your final choice, right? Okay. So this kind of thing is a thing that I want you to be able to analyze and understand. Our intuition gonna say something wrong because all this sounds about right, right? I think all these arguments sounds about right until you actually write it down, what happens, okay? So the tools that we're gonna use to analyze this is a tree. We're gonna draw a tree on what can happen. Okay, we're gonna draw the tree on what's to happen. But any question about the rule though? Any questions about the rule? Right? What we are trying to understand is what is the probability that you're winning, right? We want to answer this. Should you switch or not? Any question about the rule though? Any questions about the rule? Now what are we good? Yes, you choose. I open one card and then they ask you, do you want to switch? Yes, the right card is confirmed to be wrong by me. By me, because I know which card has a joker, right? So for example, if you pick the joker, then I have 2 choices for the non-joker card, right? Then it's clear you don't want to pick it because you want to pick the joker. Are you clear? Are we good? Right. So the question is, do you want to switch or do you want not want? But Ajahn cannot choose. No, why would I review the joker? If I review the joker, there's nothing for you to do, right? I know which one doesn't have joker, and then I'm gonna review that one. Okay. Right, because that way you have a choice. Do you want to switch or do you not want to switch? Clear. Let's draw a tree on what happens. Okay. To understand this, our intuition gonna tell you something really wrong, and it sounds so right, except it's gonna be wrong. Okay, so we're gonna use a tool to do this. It's called a tree. Well, just draw a tree, essentially. So let's think about what can happen, right? The first thing that I can do, I need to hide the joker behind it, right? But I'm gonna draw it. So let's say, without loss of generality, I'm gonna hide the joker behind A. Actually, let's draw the full tree for this one. Okay, so I have three choices, right? Start from the left though, and keep the space. Save the space. No, 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 no. I do not choose the right card. I review it. So that means I show you that this card is not a joker. And then I ask you, do you want to switch or not? I show you that this card is not a joker. I deliberately show you the one that is not a joker, not the one that is a joker. Yes. Yes. So that means you're gonna know that there is a joker left when you if you switch or not. Okay. So this is the joker is behind. Okay. Let's list out all the things that can happen, right? So there are three choices for the joker to be behind, right? A, B, or C. You can think about this as like A, B, and C. Okay. So after we hide the joker, what do? You pick a card, right? Okay, you pick a card. So you have three choices you can pick, right? You can pick A. So you pick first choice. Let's call that first choice. You can pick A. You can pick B. You can pick C, and you can pick A, B, and C, and A, and B, and C. Someone get right? You choose, and then the what's happened next is that I open a card, right? So I open a card. I review a card. Let's make it review. Okay. If the card is behind A, you choose A, right? Let me put A, B, and C. So why C is inside? So if the joker is behind A, you choose A, then I have two choices to open, right? To review to you, B or C. So there's a B, there's a C. Sounds good, right? Let me do this. This is review B. We need to save some space because it's going to be long. Review B, review C. I have two choices, right? And then B, if the joker is behind A, you pick B, then I have only one choice, right, to review C. Someone clear on that? Right? I cannot pick the card that you choose. And then I need to open the one that's not joker, so I have one choice, and the same thing as C. Okay, so let me finish this. Someone get so far though. The card chosen will be reviewed at the very end to see if you get the prize or not, right? So let's keep track. Let's keep track. What we want to keep track is the following metric, right? Okay. What we want to keep track is whether you switch and win. What we want to keep track is switch and win. So for the first one, right? The joker is behind A. Your choice is B is A, and then I open B. What is the problem? Do when you if you switch, do you win or do you lose? You lose, right? Because you pick A already. If you switch, then you screwed. Let me write it over here. Switch and win. Okay, so that's a no. Okay, so for this guy, it's also a no. Let me finish up the table. I guess everyone with me so far, right? You know, it takes me like a lot of time to type this in LaTeX, so you can look at the LaTeX on lecture note as well. This one is a yes, a no, a no, right? And a yes, 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 no, no. So that's good. On good so far, right? We can fill out this table. So let me ask you, what is the probability that you're going to win if you switch? Right? So Pong Chai or Keith says the following, Ajahn, this is easy. This is like kindergarten math. You just count number of X and the number of check marks, right? There are 6 of these and there are 12 total. So that means the probability should be 6/12, which is exactly a half. Sounds about right or not? What do you think? What do you guys think? A lot of you said in earlier, right? I will always switch because it seems like a good idea to do it. If you say otherwise, can you tell me what's wrong with this argument? What's wrong with this argument? What's wrong with this argument? We start with the joker behind A. You can start with the joker behind anything. Now what? We already covered all the cases. There are 3 cards. Yeah, there are 3 cards, and we start with joker behind. We cover every case, right? Joker behind A, joker behind B, joker behind C. Yes, there's a hole in this argument. There's a really, really big hole in this argument. What if we not switch? Well, you just count the X mark, right? You just count the X mark. So for not switch, you have 6/12 as well. That kind of worked out, right? Not switch and win kind of work out. What if you don't switch and still win? But I'm not asking about that, right? I'm asking about probability that you can switch and win. But you can calculate that it's also a half. With this argument, it's also a half. But if you think about it, the second argument is very sound, right? The fact that I asked you to choose or not should not change any probabilities if you don't listen to me at all. No, let me tell you something is really wrong with this argument. Can anyone tell me why? What is wrong with this argument? Okay, this is going to teach you something really important about probabilities. Okay, a lot of people have misconception about probability because of this property. Anyone? A lot of you say 2/3 or 1/3, right? Okay, let's think about this. This is a very important intuition that you should have. Okay. So suppose, think about this. If you buy a lottery today, let's say you go buy a lottery. Okay. Think about this argument. You either win the first prize or you not win the first prize, right? Win the first prize, win the jackpot, or not win the jackpot. Right? Are we get? Right? So if you buy a lottery today, there are two things that can happen. You win the jackpot or you don't win the jackpot. Let me ask you, what is the probability that you're going to win the jackpot? If you use exactly the same argument, if you use exactly the same argument that you had before, right? Because it should be 1/2. If you use exactly the same argument before, then you should go buy lottery right now. But you know it's a scam, right? Lottery is a pure scam. It's like poor people's tax or math, or it's called intelligence tax. Okay, is that one good? If you use exactly the same argument that you had before by counting, okay, do I win the jackpot? Yes. Do you win the jackpot? No, here. And then you count, okay, there are two, it's a half. But in your mind, you know it's clearly wrong. What Alexei said is correct, right? That, okay, Adan is actually when it has to be 1 in a million, because when you calculate the probability, it's not the outcome over the outcome, is each of the outcome has the associated probabilities, right? 10, it's actually 10 to the 6. Are we good? So when we did it here, when we did by counting the check marks and the X marks, we did not take into account the associated probability of each of the outcome. Are we good? Right? We did not take into account the associated probability of each outcome. We only count the outcome, right? It's like either you win the lottery or you don't. But that doesn't mean your chance is going to be a half. Okay. So for each of the outcome, we're going to call this the outcome, right? That is the associated probabilities. And let's do that together. Let's calculate the associated probabilities. Okay. So let's say I hide this. It actually doesn't matter for this number. I hide this. There's a 1/3 chance that I'm going to hide it under A. A third chance I'm going to hide under B. And a third chance I'm going to hide under C. Okay, so that's good. Right, a third chance that I'm going to hide it. And for the choice, then every one of you, let's say you do it randomly, right? You have a third chance of like putting everything there. No, we're not done yet. We're not done yet. Okay. And then if the joker is behind A, and you pick A, I will B or C. What is the probability of each one of them? What's the probability of each one? That is going to be a half, right? It's going to be a half. Okay. What about this guy? What about this guy? B to C. What's the probability? It has to be 1. Okay. Now that is the difference. We get, and that's a 1. That's a 1. That's a half. That's a half. Let me fill this table. That's a 1, 1, 1, a half, and a half. Now we can calculate the associated probability of each one of them. Are we good? So what is the associated probability of this outcome of this AAB? What is the associated probability? What is it? Can someone tell me? It's 1/18, right? So what you do, you just multiply all these numbers together up until you get to the end. Okay. And for the next one, it's also 1/18 if you calculate it. And this thing is 1/9. 1/9. 1/9. 1/18. 1/18. 1 over 9, 1 over 9, 1 over 9, 1 over 18, 1 over 18. So that's good. So how do you count though? How do you count? What's the probability that you're going to switch and win? Let's do it correctly this time. What would you do? What would you do? The probability that you're going to switch and win, what would you do? Right? You add up all these, the one that you switch and win. Okay, there are 6 of them, right? So there are 6 times 1 9, so it's 2/3. And also you can do it the other way as well. Probability, not switch, let's call it stay and win. It's going to be what? 6 times 1 over 18, which is 1/3. Are we good? Right? So you know, which sound quite unintuitive, but if you think about it, it's actually correct. So the question whether you should switch it or not, it is that you should, because it's 2/3 probability that you're going to switch and win. Okay, are we good? And you may ask, Ajahn, so what's wrong with the other argument with 1/2? The thing that is went wrong with this argument is the fact that you associate the number of outcomes with the probabilities, which they are not. This is the same argument as you either win the lottery or you don't, but you take that, it's 1/2 each. It's actually not 1/2. Okay. Any questions so far or any questions so far? Do you now believe that it's 2/3? I can actually, the review is irrelevant. Actually, no, the review is actually not irrelevant. Think about this. Think about this. Here is the intuition I want you to have. But again, I said intuition is always wrong. But this is a good way for you to convince, for me to convince you that it's 2/3. So I say that if you stay, right? If you stay, you are picking one card. But if you switch, you are effectively picking 2 cards. And then I'm going to open one for you anyway. Right? It's like you pick 2 cards and then I'm going to open one for you anyway. So it should be 2/3 if you think about it. Okay, you're picking the 2 cards that you don't pick before, and then I'm going to choose which one to open for you. Okay, so your chance should be 2/3 if you switch and 1/3 if you don't. Is everyone good? Okay, any questions so far? Any questions so far? Any questions so far? Any so far? This was a scam, and actually you're gonna do a version of this scam in your homework. It's homework 7 though. Do homework 6 first. Homework 7, there is a lot of scamming game. I asked you whether this is a fair game, but you know, most of the time it's a no in this class. Most of the time, the game is not fair. Life is not fair, but Ajahn is cheating. Okay, so let's do this. Let's do this. Let me define the probability based on what we did. Based on what we did, right? So you're gonna be surprised how people define probability. But in the back of your mind, right, there are 2 things. There are 2 things that you should think about. There is the outcome. Okay, the outcome, that is like the event, right? It's like the fact that the Joker is behind A, right? The Joker, and I open what? I open A, and then I wait. You pick, and then I reveal B. Okay. Let me put up the lecture note. Let me make sure that I use the same word, or else I'm gonna confuse you and myself. Let me make sure I use the same the same vocabulary. 2 seconds. I'm really bad at like definition and what things are called. Let me make sure that I use the same one, blah, 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 blah. Okay, I call it the outcome. Okay, good. Did you hear my daughter? Okay, so yes, now it's not freezing anymore, right? So there is, because I was switching the screen to see that I use the same word. This is called the outcome, right? There are many things that can happen. You can pick A, C, and I open what, B, right? Or AAC, that's a valid one too. The outcome are like the things that can happen. So the set of outcome, what did it? Let me make sure I use the same word. Wait 2 seconds. Okay, so the set of outcome is called the sample space. Okay, what did you write below? So the joker is behind A, you pick A, and then I review B, right? So sample space is like, if in the case of lotteries, right? In the case of lottery, there's going to be either you win or not win. Are we good? Or in the case of multi-hole problem, it could be AAB, AAC, ACB, and so on. But no AAA, by the way. No AAA, because that is not according to the rule. Okay, so far so good. But you see, sample space is not enough to do the math, right? You need the associate probabilities. Okay. So typically we call this omega, little omega, and sample space I use S. Are we good? I want you to get not the formal definition, but I want to get you the intuitive idea behind what an outcome is. So outcome is what could happen. What could happen without the associated probabilities. Okay, and most people do it this way, which is wrong. Okay, so that's a good, right? Then, if you really want to calculate some meaningful statistics, okay, or meaningful probabilities, then you will need another function, which is the probability function. Okay, it is a function. Probability is a function, by the way. A function that takes in omega, that is in S, and then takes in an event, right? It takes in an outcome, not an event, an outcome, and it split out a float, a real number. Okay, which is the associated probability. So for example, so P of win the lottery, that is 10 to the minus 6, right? P of not win the lottery is going to be 1 minus 10 to the minus 6. Are we good? So the probability is like a function. You can think about it as a hash map as well, because Saran just learned it. You can think about it as a hash map, but if you have infinite number of things, and hash map doesn't work anymore, so you need a function. Okay, a lot of you just learned that in a Kanat's class, what a hash map is. It's probably one of the best data structure there is. It saves you a lot of big O's. Okay, probability is a function that takes in the outcome and it split you out the probability, but there is a certain restriction that the sum, okay, but the sum of all the outcome of the probability is going to be 1. Okay, and there's some restriction that probability can be negative and so on as well. And also that P omega is greater than or equal to 0 for all omega. Any questions so far though? We learned 2 things, right? The outcome, which is what could happen, and the probabilities. Okay, A probability is just a function. Any questions so far though? This is just a definition for you to get the idea. There's a formal definition in the lecture note if you want to read. But the idea is the following, that you have things of list of things that could happen and the associated probability for each of the outcome. It's like this guy. So this is the probability associated with each outcome. Okay. What time is it? Any questions so far though? If not, we're gonna take 10 minutes break because I want to teach you something really cool next. And it's gonna take a while. Anyone? Anyone has a question? If not, let's take 10 minutes break. So come back at 14:53. Oops, and I sent to Keith only. 14:53. 14:53. Yes. Trust me, everyone's struggling on the midterm. Like I said, if you know what you're doing, it should take you 2 to 3 hours. But take as long as you need. I turn off the microphone. What? What is an Elsa? The one obvious question to make a solution roughly. To answer Justin, yes, you can make it as long as you like. Like you can add another page. It's okay. You can add the extra page if you like. Okay, so let's continue on what we learned, right? We learned about probability that it has to do with the outcome, and then the associated is in the associated probabilities. So let's look at another problem, which will give you like will prevent you from using your intuition on probabilities. So I kind of not recommend you to use your intuition here. So let's consider the following problem. You have three dices. Oops. Three dices. It's a fair dice. So each face has a probability of showing up equally. So let me get the number real quick. 267. A is 267 and B is 159, right? 159 and C has 348. Okay, there are three dices. Okay, each one can turn on each of the number and it's a fair dice, so it's 1/3 each. 1/3 each. 1/3 each. The game is simple. The game is simple. You can make it 6 sides and make it double. That works too. Right? 3 sides, you don't know how to put that kind of thing in to 3D. And I'm not sure. Maybe there's a way. I'm not sure. Okay, so there are 3 dice and each one of them has like number associated with it. The game is simple. A, pick a dice. Oh, I call someone A. Alpha, pick a dice. Beta, pick a dice. And whoever rolls higher number, right? Higher number win. So for example, if alpha pick A and beta pick B, and then alpha when it rolls, he gets 2, and beta when he picks B, he rolls, he gets 5. So that means B wins. Okay. So the question that I have for you is, which dice is the best? Which one would you pick, A, B, or C? Which one would you pick? A, B, or C? C, A, B. Okay, that's great. Now, so let's say, okay, there are 2 people here. There is Nawat and Saran over here. You like it, the soup. And there's a Justin here. And there's a Josh here. Okay, let me pit you all against each other. You can pick. No, you cannot pick D. It doesn't exist. Okay, so let's wait. Time to see who the real alpha is. Okay, let's play A against B. A versus B. Okay, we're gonna calculate the probability that A is gonna win against B. Probably that A wins against B. Okay, let's calculate that. Okay, and is it greater than half, then A is better. Everyone clear on that, right? Okay. Okay, that's it. I'm going to remove you for a second. So A versus B. So let's do this. when you toss A, there are three choices. It's 2, 6, and 7, right? We use the 3 again to, to understand this. And after you do that, there's a 1, 5, and 9, 1, 5, and 9, and 1, and 5, and 9, right? And each one of them has an associated probably is 1, 9. I think that's clear. Okay, so let's do this. A wins, right? Then you compare this number against this number. If it's greater than A wins, A wins. Yes, no, no, yes, yes, no, and yes, yes, no. So what's the probability that A wins against B? No. Count carefully. Count carefully. 5/9, not 2. 5/9, guys. 5/9. Okay. Is someone clear on 5/9? 5/9, right? So we can say that A is better than B. Okay. Again, what? So when you toss a dice, right? So you compare, you do the 3 again. This is what A gets. Oh, I forgot to write here. This is what A and this is what B gets, right? And then all we need to do is count like how many of them, right? Because every one of them has associated probability of 1/9. So just count. Okay, there are 5 spots where A wins and there are 4 spots where A loses. So probably that A gonna win against B is 5/9. As simple as that. Okay, so now Justin is back. Justin is back. I need you. Okay. Okay. So now Justin is back. Let's do Josh versus Justin. Okay. Because A kind of wins already. Let's see. Let's see if Josh win or lose against Justin. So let's do B versus C. Let's do exactly the same exercise. Okay. So B is 1 and 5 and 9, and C is what? 3, 4, 8. Okay, let me write this. 3, 4, and 8. 3, 4, and 8. And 3 and 4 and 8. Okay. And say, let's count how many of them B wins. Okay. So this and that, no, B lose. This and that, B lose. This and that, B also lose. It's gonna win, win, lose. Right. And then win, win, win. So which one wins? Probability that B wins C is how much? It's also 5/9. Which means we learn two things, right? That okay, I maybe Justin is the worst, right? A is better than B and B is better than C. So what do you think happens if I get A and C to play each other? What do you think happens if I get A and C to play each other? After we know this, what do you think? Yes, we're gonna do the 3 thing again, but guess first. So A should A win or B win? C win? C wins. Okay, let's do the 3. Let's do the 3. Let's do the 3. Good for you. That means you learned something in this class, therefore to use into your intuition. So C is gonna be 3, 4, 8. Do the 3 thing again. Okay, and say A wins. Right, let's count. Does A wins? This is A, this is C. No, no, no. Yes, yes, no. And yes, yes, no. So probability that A wins C is how much? It's 4-9. Right? Doesn't that sound weird? Because we kind of know the following, right? A wins against B, B wins against A, but also, against C, but C wins against A. Doesn't that sound? Have you seen this kind of thing before, though? Is it Pokemon? Yes, because you guys are like what your generation is called, whatever the name is. Yes, but in my generation, it's called rock paper scissors. But yes, it's a Pokemon. And actually, that's how Pokemon is designed. It's designed to be rock paper scissors, so that you can counter the other element always. Right. So this is actually the game design. StarCraft or any good game. Any good game will not have the obvious choice on what is the best, right? You can always counter the other guys, always. Right? And this is a good game choice. So this is the rock, paper, scissors. There is also the version that there are 5 of them, and then there's the version that there are 6 or 7 of them. In the end, it doesn't matter. Yes. So in the end, it really doesn't matter. But you know which one wins against which one, right? So the probability doesn't have the transitive property. So if A wins B and B wins C, it doesn't mean that C wins A. So no transitive. You can actually buy the dice. This set of dice is called non-transitive, right? Dice transitive. Dice, you can buy it on Shopee, I think. No one sells it. I'm pretty sure. We 3D printed it, but it's at school. We 3D printed them, but it's at school. Okay, any questions so far though? Any questions so far? Okay. If no question, in your homework, you're gonna find something really weird. Let me ask you about another game. Same dice, ABC, which you know that it has that properties, right? What's the number? 267, 267, 159, and 348. Okay. In the homework, you're gonna show that if I ask you to pick a dice, the same thing as you did, right? If you pick A, but I ask you to toss it twice. So that means A plus A versus B plus B versus C plus C. By that, you know that A is better than B, right? And B is better than C, and C is better than A. Let me ask you, A plus A and B plus B, who do you think gonna win? A plus A means you toss A twice. You toss A twice and add up the faces. Exactly. You're gonna find that it's exactly the opposite. You're gonna find that it's exactly the opposite. You're gonna do that in the homework. You're gonna convince yourself in the homework. You're gonna do that in the homework. Okay? And that's why you want to do the homework. Because you're like, come on, this can't be true. But yes, it is true. Draw a tree in a smart way. Then you're gonna figure out how to do it. Draw a tree in a smart way. Okay? So for example, okay, in a smart way means the following. So for example, the tree that I drew you here, what I really want is only the first branch, right? And then I multiply everything by 3 or something. You know what's a good idea? Write a code to generate the tree and then get LaTeX to render the tree. There is a thing called network X. The answer for all your graph theory that you take in Ajahn Kanat and Johnson Cert is network X. But you're gonna write it on your own like one or twice in your life, and then you're gonna use the library for the rest. Okay, so the next thing that I want to show you is that the sample space, right? We learned the probability space, space is the sample space. Remember, these are the outcome and the probability function. Okay. So what the next example that I want to show you is to show you that this sample space, what we have so far, right, is limited, is finite. What that means that, so for example, you have this thing is 2 and 3, right? The outcome is 2 and 3. The outcome for here is 2 and 4, but you have like 9 of them, a finite number of them. But the sample space could be something infinite. Let me give you an example. An example would be the game where you toss head or tail, right? You toss a coin, head or tail. Okay. I toss the coin, head or tail. And then we're gonna toss, and then the game say toss until you get a head. So far so good. So if you think about your sample space, right? Your sample space is going to be the set that, okay, you may get head on the first try, or you may get head, tail, then head. Okay, or you may get tail, tail, then head, or tail, 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 then head, or tail, 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 then head. But you know that you could do it infinite number of times. Is everyone good? Right? You could do it infinite number of times. And let me ask you the following. Okay, this is a sample space, and you know that this thing is infinite. This thing is infinite. I asked you the following, okay? That what is the probability that we're gonna play even number of time? Okay, so that means this guy counts, that guy's count, not this guy, not that guy, not that guy. Okay, so what should we do though? What should we do? How should we like approach this kind of thing? What else do we need besides the sample space? What else do we need? You need the associated probability, right? Remember, if you try to calculate something, sample space is not enough. So you cannot just count this, right? You cannot just count the outcome and then divide by the total number of things in the set. It doesn't work that way, right? You need the associated probability. So let's find that out. Okay, the associated probabilities is what is the probability they're gonna toss head the first time though? If the coin is fair, it's a half, right? So the associated probability of this is no, not a fourth, a half. Okay, and the next one is a fourth, right? This is an 8. This is a 16. This is a 32. That sounds familiar, right? So the question is, right? Then we are asking that you only get to play even number of times. So it's clear, right? So probability of getting each one of them is a half. Okay. So we want to ask about the probability that you get to play even number of times. Okay, and this kind of thing, the official word is called the event. Okay, so event is a subset of the subspace. What that means the following is it's just some event we count, some event we don't, right? This event is going to be tail head, tail, tail, tail head, and so on, right? So the probability of event, I think that's clear that you just need to add up all the probability of each of the item. Okay, so how do we do this? What is it equal to? What is it equal to? 0.5. I can tell you it's a no because okay, so it is going to be equal to the probability associated with this guy, right? 1/4 plus 1/16 plus 1/64 plus 1 over what? 256 plus so on, right? Can you tell me what this guy adds up to? Make sure you know this when you do the midterm. Maybe you don't need it, or maybe you do. I don't remember the midterm anymore. So how do we do this? How do we do this? Yes, it's a geometric sum. So what do we do with the geometric sum? How do we solve the geometric sum? Square it. No, square it. You on the right side, you have infinite number of terms. If you square it, then you get like infinite square number of terms. Good. So you set it equal to p, right? And then you say 4p is 4p is going to be 1/4, right? That thing go to 1/4 plus 1/16 plus 1/64 plus dot dot dot. Oh, I forgot the one. Sorry. So you get 4p is 1 plus p. So that means p is how much? Can you tell me? How much is it? 4p is 1 plus p. So it's going to be 1/3. Thank you very much. Right. So we can calculate the probability of an event, right? Event is not, it's just a fancy word. It's just a fancy word. You don't really need to know that there's a thing called event, but just need to know that it's a probability of set of things that you care about. Okay. And you can calculate it by adding the probabilities. Okay. So because we almost run out of time, let me finish off with a few things. Some obvious thing about probabilities that let me spell out. Okay, some obvious thing. So how about this? If we know already the probability that you are, so why we multiply this by 4? Because when you multiply it by 4, you get almost back the same thing. Right? Then you get this. Or the geometric series. Okay. Okay, so we learn probability end up play even and multiply. Okay. What do we know? And we know that this thing is 1/3. What do we know about probability that we don't get to play even number of time? Not play even. What do we know? How do we calculate it? How do we calculate it? What do you think? Good. So this thing is going to be 1 minus the whole thing, right? So either you get it or you don't. So there. So probability of not something is the probability is 1 minus probability of that thing happens. So if you want to be more fancy, is P of not A is 1 minus P of A. Okay. That's good. Now, how about this? How about this? Remember that I say that A, an event A, this is an event, this is a set. of outcome, which means I can do a whole bunch of things with a set, right? For example, I want the probability that we get to play even or play more than 10 turns. Okay, right? So that means this is like a union, right? There is a set of outcome that you play even number of turns, and there's a set of outcome that you play more than 10 turns. Okay, so that means this thing is like P, A, union with B. Okay, so let me draw you the usual diagram. Right, there's this guy A, there's this guy B. Okay, what is it equal to? If I do this, I think it's so tempting for you to do this. It's a probability of A plus probability of B. What's going to happen? If I do this, what's going to happen? You overcount. Where did you overcount? You overcount the intersect, right? I do this. So how do we fix this? How do we fix this? So that we count it correctly? Good. You just subtract off P of A and B. Okay. That's another rule that you learn, but you can get it by drawing a picture in 5 minutes. Okay. And what else do I have? Okay, there is also another one, which is probability B, probability that I play even, but not more than 10. Okay, so let me draw you the diagram on exactly what we want, right? So this is like P of, I can say A minus B. Okay, this is what it looks like. Okay, so this thing is A and this thing is B. What is it equal to? Can you tell me? So what we want to count is this green. Oops, it's this green, right? A minus B looks like this. Okay, so you play even, but you do not play more than 10. So what is this guy equal to? Good. You can start with A, right? P of A, and then you minus the thing that you don't want to count. That's another rule. And do I ask you to like memorize all these rules? No, because you can draw it and get it in 5 seconds, right? Just draw a picture, then you're gonna see what you need. Are we good? Yeah. Any questions so far though? Any questions so far? There is a union. Still one. Okay. So don't bother memorizing. Don't bother. Okay. There is a thing I want to teach you, but it's gonna take more than 20 minutes. That's the thing I want to teach you, and it's gonna take more than 20 minutes. Okay, I'm gonna end the class here then. It's gonna take more than 20 minutes, and it's better if I teach it like in a self-contained class. It is the conditional probability, which is the basis of all the machine learning. It's better if I teach it in a self-contained class. Will we be having last week on campus? I don't think so. Is there a announcement? Or I can pick something from this book. This. Look at this. It say if A beats B and B beats. So we just learned that like 5 minutes ago, right? It teaches you how to bluff in poker game. I'm pretty sure there's a PDF version of this. Look online. It's a book called Dover Book. Let me find where Dover is. Where is it? When you see the book that says Dover over here, it means it's a cheap book. It means it's a cheap book. Wait 2 seconds. It says Mr. of the game. Yeah. Let's call it a day, then I'll let you do the midterm. I'll let you do the midterm. Any question regarding the midterm though? The midterm is due on Sunday, and please do it. Don't fail. Because there are only 17 of you left. I don't know what happened for the rest. Midnight. I think I said it at midnight. If it's not midnight, then scream and complain to me. It take you 2 to 3 hours for those of you who started already. Did someone hand it in already? So that's it for today. Then, because the next thing gonna take a while. Proof by counter example is called disproof. Yes, that works. If you want to disprove something, give me a counter example. Wait, again? Okay, sure. What do you need? Let me stop recording somehow.